السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. At the end of last lecture, we started to talk about Perceptron, I think very quickly in the last 5 minutes. Today, inshallah, the whole lecture will be on Perceptron and probably the next one. So what is the idea, or what is the motivation behind Perceptron? Why we need a new model? I think last time we motivated this already. We said that sometimes we need to give weights to features. Sometimes we don't need to use all features equally, or even to say these features we would use and all the others not. We need a mechanism to say we want many of the features, but in different priorities or in different importance. So the main idea here in Perceptron is to learn weights for features. So every feature will have a weight. We will need to learn a weight for each feature. If the weight is high, then this feature is more needed or more useful in classification. If the weight is low, close to 0, then that means that it is not useful. Okay, so that's the main motivation. Now, what is the inspiration for Perceptron? It is actually a biological inspiration from our minds. So our brains consist of a bunch of small units called neurons. And these neurons are connected somehow. Some neurons are connected to other neurons. And each neuron sends electrical signals to others. Okay? So it receives signals from others through what we call dendrites. Let me change this. Okay, so it receives signals from others through what we call dendrites, and it sends signals to others through what we call axons. So there is input to the neuron, and there is output from the neuron. Okay? And neurons actually are connected with each other. But the connections are not all of the same strength. Some connections are strong, some connections are weak. Right. In Perceptron, we model one neuron only. We don't model so many neurons, we just model one neuron only. So if we look at one neuron only, we have multiple inputs. If we look at one perceptron, we have inputs to the perceptron from other neurons, and we have output from the perceptron, from one neuron, I mean. Okay, we call one neuron perceptron. So if we look at this neuron in particular, it has inputs from other neurons, and it has one output which is sent to the other neurons. Right. We need then to have a mathematical model for this one neuron. Before doing so, let me tell you that when the neuron sends a signal, we call it an activation or firing. So the neuron fires based on the values of the input signals to it. Okay, so the amount of activation or amount of firing of a neuron depends on two things. Depends on how strong the signals are from the input, and how strong are the connections that those inputs are going through. We said that neurons, there are connections, right, between neurons, right? So the value of the activation for one neuron depends on how strong the activations of the other neurons and how strong the connections are to that neuron. Now, if we understand this, then we can model it that way. We have multiple input signals. The input signals here, we call them x1, x2, up to xn. And these signals go through connections, right? One connection per signal. And the weight, so the value first, the value of the activation of each signal is x1, x2, up to xn. And the strength of the connection is indicated here by W's. So the strength of the first connection that x1 goes through is W1, and then W2, and so on up to Wn. Every input signal goes through a connection, and that connection has a weight, which indicates the strength of that connection. Okay? The input signal itself has a strength, which is the value here, which is x's. So x's are the activation from the other connection, from the other neurons. The weights here are the strength of the connections. Type. The activation of the neuron that we are modeling is a weighted sum of the activation of the incoming signals. So we just multiply each value of the signal to its weight, and then sum all together. Okay, we call this the activation value, or the activation in short. Type. Is that the output of the neuron? No. This activation value, if it is positive, then the neuron will be activated, or will fire, will send the signal to the external world. If not, then it will not fire, it will not be activated. That's why we have a step function here. If the input to that function is positive, then the output will be 1. If the input to that function is negative, then the output is 0. Okay? That's a model of one neuron. So in summary, the neuron is connected to other neurons. They are sending signals to it. The strength of these signals and the strength of the connections through which these signals are sent affects the activation of the neuron. How we model it? We model it by this weighted sum. So each signal value is multiplied by a weight, and then the sum is the activation value. If that activation value is positive, then the output of the neuron will be 1. If not, it will be 0. And when it's 1, we said that it fires or it is activated. That's a neuron. Now, in the context of classification, what is all of that? The input signals are the feature values. So each one here is a feature. And x1 is the value of the first feature. xn is the value of the nth feature. Okay? The weights are the strength of the connection in classification is the weight that we give to each feature. Remember, we said that perceptron, the main idea is to learn weights for features, right? So there is a weight for each feature. Okay? And the output will be the predicted label for that example. So we give an example in terms of feature values, and then the output of the neuron will be 0 or 1. If it's 1, then the predicted label is positive. If it's 0, then it is negative. Okay, so that's the model of perceptron and how it looks like a classifier. Yes?
So each of these X are a feature?
They are values for features. Yes, so you can think of it as a value for one feature, each one of them.
But if you're assigning weights, then what's the point of weighting all of it?
We are giving a different weight for each feature. So all of these weights are different.
How are we assigning these weights?
That's how we will learn the model. We'll come to that. Okay, that's how we train the perceptron. Okay, but this is how it works. Okay, any other questions? Yes.
The output is the label?
Exactly, the output is the classification or the prediction. Okay, the output of that is the prediction. It's either positive or negative, which means that this perceptron is binary classifier. Very good. Okay, it is a binary classifier. It gives only positive or negative. Okay, yes. We'll talk about that later. Okay, but the standard perceptron is using a step function. Okay?
Mathematically, step function.
Yes, it is a step function. What do you mean by mathematically? Everything here is mathematical. Okay? Now you understand the idea, the main motivation. Then you understand how we put it in the context of classification. Right? Right. Now, in reality, perceptron has one additional thing, which is called bias. Okay? So the bias is one value, which is added to the weighted sum. Now, the activation value is not just the weighted sum. It is the weighted sum plus the bias. Okay? Type. What is the meaning of that? without the bias, when will be the predicted value to be positive? If the weighted sum is greater than 0, right? Right? Type. If we want to change this threshold, then we can add b, so that when this as a whole is greater than 0, that means that the weighted sum is greater than minus b. So this is a way to control the threshold of firing. And instead of the threshold to be always 0, then we can control it. We can say, okay, if it's greater than 3, then it will fire. Or if it's greater than minus 5, it will fire. Okay, so that's a parameter now. Okay, so we add it to be more flexible in terms of the threshold of firing. If A is weighted sum is equal to 0, then it depends on the value of B. If B is positive, then it will fire. If not, then it will not. Okay. Type. Now here's an example. I want you to go through it. We have 3 input. We have 3 features, right? So n is the number of features, right? So we have 3 features, and here are the values of the features: 1, -1, 3, and here are the weights of the features: -1, 2, 3, and the bias is 0 in this case. What will be the activation value and what will be the predicted label? How can we do it? We just compute this, right? So how do we compute this? We multiply x1 by w1, right? So we have 1 times -1 plus -1 times 2, which was -2, and then plus 3 times 3. What will be the activation value? 6. Okay, so the activation value is 6. What is y hat? Y hat is the output. What is the relation between y hat, which is the output, and A? Y hat is applying the step function on A, right? So if A is positive, then y hat is 1. If it's negative, then it is 0. So what will be the value of y hat then? 1, right? So this is A is 6 and y hat is 1, which is the output of the neuron. Type. If B is -7, y hat will be 0. The output will be 0. Type. If B is -4, still 1, right? Still 1. Okay? It's still 1 because the activation will be still positive. Okay? Sorry? Yeah, A is called the activation value. So if B is -7, we will add -7 to 6, which will be -1, right? So the output will be 0 in this case.
Is an A equal to 0?
No, if A is 0, then it will be negative. It is positive only if A is positive. Okay?
Doctor,
Yes.
the fact that we are adding a bias, isn't this whole thing a bias now?
Isn't what?
Isn't this whole thing a bias now?
No. Actually, the bias is a parameter. We will learn it.
Like,
Okay, so we will learn. Sometimes the bias might be 0. We will see how to learn, because I know that your next question is how to learn. We will see. Okay, but it's a learned parameter. Okay, so it can be any value. Any questions so far? Okay, very good. So how do we do the prediction based on what we saw? We have the feature values. We multiply them by the weights. Okay. So and add the bias. That will be the weighted sum, or the the activation value. Then based on the activation value, the output is determined. Okay. Right. What are the parameters in this model? The parameters are the things that we learn, right? That we learn. What do we learn here? Do we learn the x's? No, these are the feature values, right? This is input to us. Do we learn the weights? Of course we learn the weights, right? That's actually the purpose of this model. We need to learn a weight for each feature. Okay? So weights are parameters. How about the bias? I just said it, right? It is also a parameter. So the parameters here are the weights and the bias. Anything else? Is the predicted value a parameter? predicted value is a parameter? Of course not. That's the output of the classifier. How about the activation value? Is it a parameter? No, it's a function of the others, right? So it's not a parameter. We don't learn the activation value. It is a fixed function of the others. So the parameters here are the weights and the bias. Type. How many parameters we have? Only two. The weights and the bias. The weight is just one parameter? Really? N. What is N?
The number of x's you have.
What's x's? The features. Okay, so the number of parameters here is not 2. It is the number of features plus, which is how many? One only. One only. Okay, so the number of features plus 1, that's the number of parameters. And of course, the prediction will be determined by the value of the activation. If the value of the activation is greater than 0, then the label is positive. So that's how the prediction will work. Okay, that's very easy, right? So you have the feature values of the example that you want to predict the label for. You just get the weighted sum, you add the bias, then check if it's positive, then the label is positive. If not, then the label is negative. Right. What remains? How do we? What is remaining now? Are we done with Perceptron? What is remaining? How do we learn? Right? How do we learn? So what is the algorithm for learning? So that's the next step. Any questions so far? Right. How do we learn these things? First, before we talk about the details of the algorithm, a couple of things about the algorithm itself. The algorithm that you will see in the next slide is called an online training algorithm. Why is it called online training? Because it updates, we update the model by seeing one example at a time. Okay? We don't update the model after seeing all the examples, like in decision trees, for example. Right? With decision trees, we get statistics from the entire training set, and then we update the model. Here, we will see that we can update the model by seeing just one example. Actually, we consider one example at a time. So that's called online training. The training algorithms that look at the entire training set before updating the model are called batch algorithms. Batch, they take the data in batch. Okay? But the other one is online, it takes one example at a time. So that's one. The second one is that it is called error-driven. The algorithm, the training algorithm or the learning algorithm that we will study is called error-driven. What do we mean by error-driven? We only update the model when it makes mistakes, when there is an error in predictions. If there is no error in predictions, we don't update the model. Okay? And the errors you'll see, the errors with respect to the training data, the training set. While we are doing training, we go through the examples. If the current model is getting the correct label for that example, we don't do any updates. If it's getting the incorrect label for that example, then we update the model. That's what we mean by error-driven. Okay?
Using the loss function?
Sorry?
Using the loss function.
The loss function here is the standard 0-1 loss function that we saw before. Yes?
What do you mean by updating?
Okay, what do you mean by updating the model in general? Any machine learning model. When we say we update the model, what do we mean by that? We are adding features? We what? We retrain? No. Update the parameters. Change the parameters. What is the model in machine learning? The model is the values of the parameters. When we say update, we are updating the model, we are changing the values of the parameters. Of course, hoping that this will make the model better, more accurate. Okay? Did I answer your question? Who was asking? Did I answer your question? Not really?
No, because like when we train, we're updating the parameter.
Yes. That's equivalent to updating the model. The model is the parameters.
Yes, but how it's training, it's getting, as it's getting more examples, it's training more, right?
We'll see the algorithm. When you see the algorithm, I think you will understand it. Okay. But in general, when we say we are updating the model, that means we are updating the parameters, okay? Because the model is the parameters, nothing else. Right. Now I think we are ready to see the training algorithm. First, what is the input to the training algorithm? We have two things. D is the training set, right? And then there is another parameter which is called max iteration. That's how many iterations we will go through the entire training set. Okay, because you will see that we will be able to actually go through the examples multiple times, not just one time. Type. At the beginning of the algorithm, lines 1 and 2, we are just initializing the parameters. We have weights. How many weights we have? Depending on the number of features, right? So here the number of features is D. That's a bit confusing in this algorithm, by the way. You see these are two different things. There's D in bold, which is the training set, and D that is not bold and italic, which means the number of features, okay? Dimensions, number of features. Yes?
What do you mean by the first D is the training set?
The training set. The examples in training.
The number of examples.
No, D is the entire training set. It's the list of examples. No, it's not a number. The bold D is not a number. The unbold D is a number. Okay? It's not my choice. It's the author of the textbook. Okay. Anyway, but you got the idea now. Right. We are initializing the weights to 0. All the weights to 0. So we start by all the weights and the bias to be 0. Okay. Then we have two nested loops. The outer one goes from 1 to max iteration. So each iteration in this loop, we will go through the entire training set. Okay? Now let's focus on the inner one, because the inner one will go through one example at a time. Every iteration in the inner one, we go through one example only. So you will see for all examples in the training set. Now, why do we have X and Y here? X is the input example, and Y is the label for that example. Remember that we are doing classification, right? So every example is labeled. So Y is the actual label for the example X. Right. What do we do with that example? We will use the current model to predict a label for that example, to see if the model now can predict the label correctly for that example or not. How do we do the prediction? In Perceptron, we compute the activation value, right? So how do we compute the activation value? The weighted sum with the current. Remember that we are using W here, the current model, the current parameters that we learned so far. So we compute the weighted sum, we add the bias, that's the activation value. Now we want to know if the predicted label now will be similar to the actual label or not. Okay, how can we do that? If their sign, the sign of them is different, then they are different. One thing that I forgot to mention here is that Y here, the label for each example, is either +1 or -1. Okay, so we assume that it's positive or negative, +1 or -1. +1, of course, for positive, -1 for negative. So if the sign of A and the sign of Y are different, then the predicted label will be different from the actual label, right? And for example, if A is negative, then the predicted label will be negative, right? Right? Then in this case, if the actual label is positive, then that's an error, right? So if we to check, now the signs are different, so there is an error in prediction, right? So to check if we have error in prediction, we can just multiply these two values together, because positive times negative, one of them will be positive and one of them will be negative in case they are different, right? So if we multiply these two values together and the value of the multiplication is negative, that means that one of them is positive and one of them is negative, right? Which means that they are different, which means there is an error in prediction for that example using the current model. Okay? Now it's the time to update the model. So if y times a is less than or equal to 0, which means that it is negative or 0, then we will update the model. So lines 7 and 8 are updating the model, which means we are updating the parameters. So line number 7, we are updating the weights. Line number 8, we are updating the bias. Now let's look at what we have here. We said that the value of y is either plus 1 or minus 1, right? So if you look at this equation, this is an equation that, that is for every weight. So for every weight, in all the weights, we add to the weight the value y times the feature value. Remember that there is a weight for each feature, right? So for feature number 1, we are adding to it for the feature number 1, we are adding to its weight the value of the feature times y. Y, we said it's 1 or minus 1, right? So in reality, we are either adding the feature value or subtracting the feature value based on the value of y. Are you with me? So maybe I should. Yes.
The x, is it from the xy set?
This is what?
The x,
Yes.
is it from the xy set?
Yes, yes, of course, yes. X here, okay, X here is the example, right? It's a feature vector. Each value is x1, x2, x. I will show you now. Okay. So where's the? So this equation, we are looking at this equation now. So let's talk about the weight, the weights. Can we see the weights as a vector? Yes, right, because we have a value, a weight for each feature, right? So the weight can be seen as a vector. That's W1, that's W2, up to W what here? No, not N here, D. Okay, in this example, in this algorithm, it is D. So we have W, D. One value for each feature. Okay, so that's the vector W. Now, how about X? X also is a vector, right? Vector of what? Feature values. So we have x1, x2, and so on until xd also. Okay? Then if we see w and x are vectors, we can say that this equation, repeating it for every weight, it's an equation in vectors actually. It's w equals, or w plus w equals w as a vector, plus x if y is 1, and minus x if y is minus 1. Okay, do you see it now? You are familiar with the adding two vectors, right? Okay, so this is like that. W equals w plus y. Y is a scalar, right? It's a scalar. It's either 1 or minus 1, x. So y is either 1 plus 1 or minus 1. So this equation actually it is either adding x to the weight vector if y is 1. Y is 1 means that this is a positive example, right? And if it's minus 1, then we are subtracting the input vector from the weights. Okay, so that's the interpretation of, or that's the computation that we do in line 7. Yes.
هل necessary إنه يكونوا negative 1 1
No, no, no. There can be anything. Okay? Can be anything. The weights also can be anything. The weights or the feature values, there's no limitation. But y is the label. So here we assume that it is either positive or negative, and specifically +1 or -1. Yes. Yes.
I don't get why we're using the feature values to determine
Okay. We will do the justification later. Okay, but I'm just showing you how the update is done. Why we did it that way, we'll talk about it later. I hope today, inshallah, we'll start talking about it. Probably next time. But this is how it is done, how it is computed. Okay? So this is the update of the weights, and that's the update of the bias. Similarly, we just add to the bias the value of y. So it's either adding 1 or -1, depending on the label for that example. Okay? Type. We are doing that update because of what? Because there was an error in prediction. Okay? So the current model mispredicted the label for the current example. Example X here. So we do the update. Type. What happens if we didn't make a mistake? We'll go to the next one. We'll skip it. We'll not do anything. We will not update the model. The model will not change, because why should we update it if it made the correct prediction, right? So we only update if the model makes an incorrect prediction. Okay? That's it. We'll go through all the examples here. And I think now you see why we are doing multiple iterations over the training set, right? Because in the first iteration, we are making updates, right? Based on the predictions. Okay, we are making mistakes. Hopefully these mistakes will be less in the next iteration when we go through the examples again. Okay, and maybe more or less, or better, I mean, when we go through multiple iterations. Yes? We don't have to. Here, for that algorithm, we just go through them max iteration. It doesn't guarantee that we will correctly, the final model will correctly predict the labels for all examples. It's not guaranteed. But we will stop after max iteration, whatever this is. Okay? Type. The last thing is line number 12. What is this? These are the parameters. Yes. These are the parameters. We are returning the learned parameters, right? خلاص, we are done. We are just returning the model, which is just the set of weights and the bias. So that's all of what we have learned.
هو line 7 برضه for loop صح؟
It's like a for loop, yes. But we can do it with vector computations like that. And in Python, you don't have to do a loop, right? Just adding the vectors. Any questions? Is that clear? Is that clear? I didn't ask you. Okay. No questions? Right. Let me ask you a question. Do we have any hyperparameters?
maximum depth in the.
Because we have maximum any?
No, because it controls the other.
Exactly. It controls the learning of the parameters, right? And we don't learn it from the learning algorithm. Do we learn the best number of iterations? We don't. Okay? But whenever we assign a value to the maximum iteration, it will affect the parameters that we learn, the values of the parameters, right? It will affect the model. Right. That means that it is a hyperparameter, and can we tune it? Can we get the best value for it? Using the diff set. Okay? It's not here, of course, but that's the general concept, as we said earlier, right? Whenever we have hyperparameters, to tune the values of the hyperparameters, then we have to have a diff set. Then this is the prediction or testing algorithm. We saw it before, I think, right? All of what we need to do is to compute, of course, giving what is the input here? The model in general, right? That's the model we learned. And what's this? That's the example that we want to predict the label for. Okay, so all of what we need to do is to compute the activation value, then check the sign of that value. If it's positive, then we return a positive. If not, then we return negative. Okay, that's very straightforward. Right. Now let's switch to some interpretation. I think in 5 minutes. We'll just give an introduction of some of the decisions that the algorithm is making. Okay, we'll just introduce few notes about that. The first one is, what is the decision boundary here? Where is the decision boundary here? Let's first assume that we don't have any bias, or the bias is 0 for now, just for simplicity, until we understand really what we mean by decision boundary here. If the bias or B is 0, then we have this, right? Right. Let me ask you first to remind me, what is a decision boundary? What do you mean by decision boundary? It's not the region, it's the boundary that separates between the regions of different classes. Okay, so the decision boundary is a boundary. It's not a region. Okay? So it is a boundary between the areas or the regions of different classes. Where? In the feature space. Right? In the feature space. What do you mean by feature space? The space that we represent the vectors for the examples in. Right? The vectors of the examples are just numerical vectors, right? We can see it in a feature space because each dimension is a feature. Type. If we think about this, if that value, assuming that the bias is 0 now, right? If that value is positive, because that's the weighted sum, and given an example X, and we have a model W, or a weights W, weights vector, if that value is positive, then this example is positive, right? It's predicted as positive. If that value is negative, then the example will be predicted as negative, right? So what separates them are the examples that will give the value 0 here. That's exactly in between, right? So all the examples X that will satisfy this equation is actually on the boundary, on the decision boundary, because that's the boundary that will separate the positive region from the negative region. Okay? So we can say that this is the equation for the decision boundary. We still didn't see or didn't understand how it looks like actually, but that's the equation for it. That's if we draw this equation, or if we show this equation in the feature space, then this is the decision boundary. Okay? How do we know? Because all the points on that space, or plane, actually it would be a hyperplane in this case, satisfies or separates between the positive and negative regions. Yes.
So it's like the threshold you mentioned earlier?
No, it's not the threshold. Okay, it's not the threshold. Okay, let me, and give me a couple of minutes. Okay, so this is the equation for the decision boundary, right? You agree with me? Type. Earlier, we said that this can be seen as, actually, we said that the weights are a vector, represented as a vector, and also the features, or x's, feature values, are a vector, right? This is like the dot product between these two vectors. If we can represent this like that, W dot product with X, right? Do you remember from linear algebra what's the dot product between two vectors? It's the multiplying each pairs of values in each dimension and sum them, right? That's the dot product. So we can actually see this as a dot product between two vectors, W and X. W is the weight vector and X is the example. Type. From linear algebra, when we have a dot product between two vectors and the dot product is 0, what does that mean? they are perpendicular, right? They are perpendicular to each other. So actually, that means that, so this is the rule, two vectors have a zero dot product, even only if they are perpendicular. That means that if we look at the weight vector, all the examples, all the points on the decision boundary are on a vector that is perpendicular to that vector. Okay? That means that the decision boundary is perpendicular to the weight vector. If that's the weight vector, then the decision boundary is perpendicular to it. Because every point here, every point on that vector, if you multiply it with, point means a vector also, right? Because we can see it as a vector. The dot product between W and any point on that line will be zero, right? Because they are perpendicular, right? So that means that this is the decision boundary. This is the decision boundary. It is always perpendicular to the weight vector. Now, the space that we see here, how many dimensions we have? 2 dimensions only, right? So that means that we have only 2 features. So in 2-dimensional space, the decision boundary is just a line that is perpendicular to the weight vector. In 3D, it will be a plane. It will be a plane that is perpendicular to the weight. More than 3D, we call it hyperplane. We call it hyperplane. No, we cannot see it. It's very hard to see it. But we call it a hyperplane. That's why we say here that the decision boundary is simply the hyperplane perpendicular to W. Okay, any question up to this point? I think we need to stop here. Any questions? Everything is clear? You know now what Perceptron is, what is the background about it, I mean the biological inspiration of it, how it works in prediction, and how we learn the model itself, right? The only remaining thing, at least in the basics, is to justify why we are updating the model that way. Okay, and we'll see that inshallah next time. Assalamu alaikum.